Okay, and we'll go ahead and get started with a review of last week, which was geologic time. So, with geologic time, we discussed two different types of dating methods. We had relative dating and we have radiometric dating. So, remember that radiometric dating is where we're looking at the proportion of daughter and parent isotopes to determine an exact number age for your given rock. Relative dating is you're looking at the chronological order, not necessarily a specific uh, numbered date. So in radiometric dating, it's the absolute dating method. We're looking at half-lives of uh, your given isotopes. So when we're looking at the uh, proportion of parent and daughter isotopes, we know the half-life of that parent isotopes. So looking at the proportion, we're able to determine the age of that given rock. We want to use that in combination with the relative dating method to also determine ages of rocks, just because doing the absolute dating method is relatively time consuming and um, it costs quite a bit. So remember that in geologic time and sediment deposition, everything follows certain laws. So a couple of the laws that we went over is the uniformitarianism, which assumes that the same natural laws and physical processes that revolve and govern the universe also applies everywhere in our geologic strata. We assume the law of original horizontality, which states that sediments are deposited horizontally. Law of superposition. So an undisturbed deposited sediment, that would mean the oldest material is at the bottom and newer material would slowly build up on top. Lateral continuity states that everything is laterally homogeneous and it spreads very evenly. So we have that same layer around the entire globe, essentially. So we would continue with inclusions, cross-cutting relationships, and fossil successions. So inclusions is bits of rocks that would be included into your new material. So the inclusion is older than the new rock material. So it's similar to conglomerate, if we recall our sedimentary rocks. Those individual pebbles that are in the conglomerate are older than the age of the conglomerate itself. Cross-cutting relationship states that anything that cuts through a specific rock, that cut is going to be younger than the rock itself. So if we're looking, for example, faults or a dike or a sill, igneous intrusion cutting through several layers of sedimentary rock, that igneous intrusion would be significantly younger than the layers that it's cut through. Fossil succession states that groups of animals have followed one or another in a definite sequence throughout Earth's history. So what that means is essentially each fossil has a very specific place and time. It could cover a range, but we know what comes first. So if we have a fossil of a dinosaur versus fossil of early human, we know that dinosaurs were much later than early human. So if we were to find a dinosaur fossil at the surface and early human fossil a little bit deeper, we know that something must have happened that would cause these two positions to flip. So if we quickly review this 3D structure diagram here, we see that the youngest material is probably going to be unit T. That is, at the very surface. So and this is going to be based on the law of original horizontality and superposition as well. If we look a little further down, we see a couple of these slanted, tilted layers. So originally, these were deposited horizontally, and then there was an event that caused them to be tilted, and also cut through with the faults, and cut through with a dike, two igneous intrusions, R and M. So at a quick glance, I would probably guess that A is the oldest material in here, and R and M are somewhere in the mid-range in terms of age, since it does cut through all these different materials and starts to cut into some of the upper level sedimentary layers. Okay, so for this week, we're getting our start in structural geology. So an important question is, why do we care about structural geology? The obvious reason is we live on Earth, we live on the planet, and it's fairly dynamic. It's important to understand what is below the Earth's surface to help us better live our lives above ground. So in this image here, we have what looks to be a slope collapse. So with some structural geology, we would have done some studies to understand the type of materials that's underneath, if that material is strong enough to sustain the weight of a home. In this situation, it was not. So we have our introduction to block diagrams. Block diagrams essentially is what we quickly looked at in the review and last week as well. So block diagram is just taking a block of the Earth and pulling that out and looking at that in a three-dimensional space, or imagining it in a three-dimensional space, where we have the map view up at the very top, if we're doing a top-down view, and we have two cross-sectional views, or four cross-sectional views, if we look at this as a true block. We have an example of a cake here, where we have a nice cross-section of the cake with the slice taken out of it. So the map view of the cake would be the very top of the cake, the frosting. And then the two cross-sectional views would just be the slice that is taken out of it. So we are now able to see the individual layers of the cake. So in structural geology, we need a way to quantitatively describe the shape of a specific structure. So if you were to have a slanted structure or slanted layer, say through uplift or a fault moving it, or a slope of any type, we need to find a way to quantitatively describe it and accurately. We could have something that is tilted, but in describing that it's tilted, we need to know how much it's tilted, what degree it's tilted, what direction it's tilted. So with that, we have the introductions of geologic strike and dip. So the dip is the tilt degree and tilt direction. And the line of strike is perpendicular to that dip direction. So it would be, if you will, the axis of which that structural plane is being moved along. So now we have our folds. So if we have in a compressional situation where we have flat structures, if we were to compress them, we would start to create folds. So we would have syncline or synforms, or anticlines or antiforms. The differences between syncline and synforms, or anticline and antiforms, is the knowledge of age. In form, we don't know the age, but it takes the form of this syncline. Antiform, it takes the form of an anticline, but we're not sure of the age. So when I describe age, what I mean is, in a syncline, the centerpiece is going to be the youngest, and we have older sections moving away from that fold axis. So in a sin-form sense, we're not sure of the age yet. So this whole thing could have been an anticline that was flipped over, and that would be, it would give us a sin-form. So in an anticline, our center fold axis would be our oldest geologic material, and we would get progressively younger as we move away from the fold axis of the anticline. So once again, in a syncline, we have our youngest material in the center and our oldest towards the edges. And we notice the strike and dip symbols that are in map view of this block diagram. So the strike is the long line and the dip is the small tick in the center, and that describes the direction of dip. So if we were to look at this video, so in a compressional environment, we start creating a U structure. So this bends all the geologic materials together. And this is where we have our hinge zone, or the fold axis, and we have the two limbs of this syncline or sin-form. So recall that syncline is knowing that we have the oldest material towards the edges, and we have the youngest material towards the center of that fold axis. So as it erodes, we have our material that are being exposed, and in real life, when we're going out to the field to map a syncline or sin-form, we'll start to notice repeating patterns of geologic material, and that's usually a good indication of syncline or sin-form. So in an anticline, it's the opposite, where we have the oldest material in the center and the youngest material is moving away from the fold axis. And we see these strike and dips are now flipped in the opposite direction, where the dip is dipping away from the fold axis. So in this animation, we have our compressional environment that pushes our geologic materials to create an anticline or antiform, where we have our hinge zone or the fold axis, and then we have our two limbs on the side. And as we erode throughout time, we'll see that the older material is exposed in the center, and then the younger material is towards the outer edges. So to reiterate, syncline and anticline, we know the ages of the individual bed layers. In the sin-form, antiform, we don't know the bed ages. But it takes the form of an anticline and syncline. Right. So to reiterate, in a syncline, we know our ages. In a sin-form, we are not sure. Right. So this assumes that everything is nice and horizontal, so the compression strength, or the compression and the folds are happening in a nice horizontal range, and nothing has been tilted. But now, in the sense where things are starting to tilt or plunging, we have plunging anticlines. So there's now the plunge direction and plunge axis as well. And at the surface level, at map view, this now takes a different look. So we now start to have these V-type shapes. So we'll now introduce faults. So faults is essentially two large rock groups that are sliding past one another. And these structural blocks can be fairly large, and up to the size of your tectonic plates. So there's going to be a hanging wall and a footwall. The only exception is when we're dealing with a transform fault or a strike slip fault, where the fault is supposed to be perfectly vertical. So in a hanging wall sense, this is the part of the fault that overlaps, and the footwall is the ramp. So if you were to think about a tunnel that goes directly through the fault or along the fault, and you would be a person within this hole, the hanging wall is where you could hang your lamp, and the footwall is where you would be standing, as shown with this cartoon. So we have different fault types. We have our normal faults, our reverse faults, and our strike-slip faults. And strike-slip faults are two-directional, where they're right lateral and left lateral. So in the normal fault sense, we have our hanging wall that moves down, or the footwall moves up. And then in the reverse fault, we have our hanging wall moving up and our footwall moving down. Our right lateral and left lateral strike-slip faults are where these blocks slide past one another. So in the normal fault, if we look at the arrows, we are in an extensional environment. This is where these blocks are being pulled apart. So that means they're sliding against one another as they're being pulled apart. So it's lengthening. That is why the footwall moves up and the hanging wall moves down. In the reverse fault sense, we're in a compressional environment, and this is where the hanging wall moves up and the footwall moves down. So once again, we have our fault trace in a normal fault. We have our hanging wall that drops down, and then our footwall that goes up. And then the exposed portion of this is now called a fault scarp. Right, so if we look at this from a different point of view, we see this as an extensional environment where the blocks are being pulled apart. So we're extending the ground, essentially, by dropping the hanging wall or raising the footwall. Right? And in a reverse fault, we have something that's a little bit different, where we have our hanging wall that is pushed up, or the footwalls drop down. Scarp is what is exposed to the surface. That usually gets eroded pretty quickly. And then in a different point of view, we have shortening or compression of our ground. Right. So in general sense also, in our reverse fault, they tend to have a very shallow angle. So this shows about 30 degrees. And that's a fairly general thing that we've seen before for a majority of reverse faults. They all tend to be fairly shallow angle. Now in a transform fault, we have our fault trace and our hanging wall footwall. This is labeled as hanging wall footwall, even though in a true transform strike slip fault, we should have a purely vertical fault. So in here, in this different point of view, we see that there is no vertical offset in the side view, in this cross-sectional view. However, in the bird's eye view, or the map view, we do see that there is a transformation of the ground. So there is a shift. So in your lab, you should be drawing some block diagrams. So you'll start off with something fairly blank, such as this, and we can tell that this would be a antiform based on the first layer that's given here. And what you're supposed to do is you're supposed to fill in the rest of the sides. So we would trace that line going back to both sides. Or also, the other type of block diagram you would encounter is if you were given a fold axis, several strikes and dips, and your goal is to draw the shape, essentially. So we can tell that this would be also an antiform. So in your lab books, on page 214, this is going to be a very important page. You want to pay close attention to these map symbols. So this will tell us our strike and dip symbols, fault symbols, um, fold types, and age abbreviations. And you want to pay close attention to these when working on your assignment. So this is only half of the structural geology lab, and next week we'll continue with the part 2 of the structural geology lab.